1/2 by definition, and this is 0 by definition, and this is 1/2 by definition. In either case, we get the same results. All right. Now, let's define another notion called sample mean. Okay. Let's say we have a set of n numbers. Okay, so these are numbers. Okay. Then the sample mean is defined as this. So just sum all the values and divide by the number of elements. So that's n. So this is called sample mean. Okay, for example, if we have values 1, 5.3, negative 1.5, 4.2. In this case, the sample mean is 1 over 4 because there are 4 elements here. And 1 plus 5.3 minus 1.5 plus 4.2. That should be 2.25. Okay. So how does this sample mean relate to the expectation value? So if we make a series of n observation, we may have n values. Okay, and from which we calculate the sample mean. Okay, and next year maybe we make another set of n observations. So let's say we have x1 prime, x2 prime, up to xn prime. Then we can calculate their sample mean. Okay. It's like let's measure the temperature of some place in Brunei every day of the year. So there will be like 365 numbers in 1 year. Then we can calculate the average temperature. Okay. And the next year, we again measure the temperature of the same place at the same time every day for the 1 year. Then we have another measurement and we can calculate the average temperature of that year. In general, of course, they are different. Okay. So these values may be considered as random variables. So how do we cast this problem as in terms of random variables? So we consider like this. We introduce, since there are n measurements each year, we introduce n random variables. So these are all random variables. Okay. And in the first year, there was one outcome as a whole. So this small x1 is equal to the outcome of this random variable x1. And x2 was an outcome, the second random variable. But notice this omega and this omega, they are the same omega. Okay? And we do this up to n. Okay? So maybe this omega can be considered as the year which is picked randomly. or all, or any other possible contingency which, you know, can occur. But this can be anything actually. This omega can be anything, but it just represents some random sampling. Okay, and next year, okay, we are having a different outcome. So x1 prime is a realization of the same random variable x1, but with a different outcome from the sample space. Okay, so x2 is x2 prime is an outcome, a realization of the same random variable x2, but with a different outcome. Okay, again, this omega prime and this omega prime, they are the same thing. And same way, xn prime is a realization of this random variable with omega prime. Okay. Then we calculate the sample mean. Okay, so this was sum of all of these divided by n. So this sample mean should be considered as a random variable. I should write random variable x bar, right? So this omega is given, then this x bar takes some value. And similarly, this omega prime is given. We have, so this is, okay, we have the sample mean. Oh, sorry, this should be I. Omega prime here. So omega prime here, and that is equal to x bar prime. This is equal to x bar. Okay, so every year we have slightly different value, maybe very different values, but they are we consider them as a realization of the same random variable, but with a different input from the sample space. Okay. So we can calculate, in principle, we can calculate the expectation value of this. So expectation value of x bar, we can calculate. So let's do it. Expectation value of x bar is, by definition, x bar is 1 divided by n times the sum of all these random variables. Okay, so but this is something you should prove, by the way, but we can expand this expectation value as the sum. Expectation value of a sum is sum of expectations. So that's what we have. And each each measurement of x bar, like this one, and next year, and maybe next year, they all have different values. But it is known that if we increase the number of samples n, then their deviations should be smaller. Okay, let's say if n is 5, no, each year we can measure temperature only for 5 days. Then there every year we may have very different values of x bars. So x bars. But if we sample 100 days, then the deviation may be smaller. So this is larger, smaller. And if it goes to infinity, well, it's the deviation means deviation can be very large in any point, but on average, it will converge to some small range if we increase this n to a large enough values. Okay. Now let's define the expectation value of a continuous random variable. Suppose we have a probability space and a continuous random variable where R is some set of real numbers. Okay, well, let's say real numbers. Then expectation value of this is defined as integration of over all real numbers and x and density function and this. Okay, of course, in some cases, the range of this random variable may be limited to positive values. In that case, the integration will be from 0 to infinity. And in other cases, it can be negative infinity to positive infinity, or in other cases, it can be negative infinity to 0, or in some other cases, it can be limited to some finite values, both up and down. Okay, and let's define a uniform distribution at this point of continuous uniform distribution. US uniform distribution. So let's consider an interval from A to B. Okay, and of course we assume A is less than B, strictly less than B. Then the continuous distribution, uniform distribution, is defined by this density function. Okay, 1 over B minus A, where x is in this interval. And we write, just for convention, unif A B. Yeah, in this example, this is open here at the bottom and closed at the top to the right. But of course, you can define uniform distribution between this, excluding both A and B, or including both A and B, or any combination, like including A but excluding B, and so on. Okay? But in any case, this a and b should be some finite value. Otherwise, this density will be 0 or cannot be defined. Okay, so one very standard example is a uniform distribution between 0 and 1. Let's say 0 and 1, including 0, excluding 1. Okay. In this case, the density function will be just 1, where x is between 0 and 1. Okay. This is the very basic uniform distribution, often found in computer programs. Actually, you can generate any other continuous distributions based on this uniform distribution. Okay, let's calculate the expectation value of this random variable. So according to the definition, so we write like this: x follows uniform distribution. And since this x is defined only in this interval, so we integrate from 0 to 1, and x times the density function, but the density function is just 1, so it's just integration of this, which is 1/2 x squared 0 to 1, which is 1/2. Okay. And you must have noticed the similarity between summation and integrals. In the case of discrete random variable, we define like x pr x equal to x. And in case of continuous random variable, we defined it like f of x dx. Okay, but if you remember the definition of the cumulative distribution function, especially for the continuous random variable, we have probability that x less than or equal to x is given by this. Okay, so if you differentiate this, both sides, it will be like probability of x. Differentiate with respect to this lowercase x, it will be this. Okay. But if you remember the definition of the derivative, this derivative, okay, this is like it's a limit of this difference. Let's write x less than or x plus dx. dx is some infinitesimal positive number. Okay, and divided by dx. Okay, and this should be equal to the density function. So f of x x dx is this probability minus this probability. But this probability is the probability that this random variable is greater than x n less than or equal to x plus dx. Okay, so that means x is in this interval. Okay, for this, for simplicity, we write like this. Okay, if you write like this, then the similarity is a little more clearer. So in discrete case, we have x probability that x is to x, and on the other hand, we have integral and x pr. Maybe we shouldn't write like this. Just use this one. X in this interval. Okay, so this x corresponds to this x, and this probability corresponds to this probability. In the discrete case, it is exactly equal, right? But in the continuous case, it's not exactly equal, but this random variable is within this small interval. Okay, that's because it's continuous. So the probability that this random variable takes exactly one value is 0. Okay, so we always consider some interval, however small it is. Okay, so summation and integral, they are basically the same thing. So from now on, we usually use only integrals, but all of the things we are going to consider will be applicable to uh, discrete random variables too. Okay. Now, first, next we don't prove, but we just introduce that a very useful theorem called the law of. It's an interesting name. Law of the unconscious statistician. Statistician. In short, LOTUS. So that's law of the unconscious statistician. Okay. That is, so if we have a random variable, and if we have a function, let's say from real to real, okay, then okay, before this, we can define a new random variable, let's say y, by this. So we plug in this random variable into this function to define a new random variable here. So the expectation value of this y, in other words, expectation value of phi of x, is given by integral of phi of x and the probability. Okay. We don't prove this. I think this is so obvious that we don't even think that this is a theorem. It's almost a definition.